Hi everyone, how's it going? This is Siri and I'm back with another PyTorch video, and in this video we're going to be continuing our discussion on our temperature conversion example, and this is yet another video on this whole process. And I guess the fact that we are dealing with this sort of temperature conversion thing doesn't really matter, so you don't need to, I would definitely recommend that you watch all of the videos because it goes into each part of the process in a lot of depth. But if you just landed on this video, I guess the exact example doesn't really matter. The only thing that matters is the fact that we're using, this sort of linear relationship between the input and the output. So for example, if you have a line, a y equals mx plus b, your m is the slope, your b is the y-intercept, and, this models a relationship between x and y, or in other words, the input data sample and the output prediction. And so yeah, we defined a linear mathematical model, and we figured out that, we came to the conclusion that your weight and your bias are really important to figuring out what line best models your data. So if you had a line of y equals 4x plus 3 and that was the line that modeled your data, but your model thought, after learning based on the loss function, and it thought it was like x plus 2, right? That's wrong, and your model knows that it's wrong after it figures out what the loss is, which just tells you how far off your input and your prediction and the actual value, how different those values are. And so yeah, that we went over the model definition, loss function, how to initialize parameters, and invoke the model. So we figured out some, we just set some initial random values to our w and b, and we are now trying to, in our last video we learned how to change and update / estimate w and b so that our loss function reaches a minimum. And we also talked about what that even means, right? What does it mean to update a parameter? Well, we used a number guessing game to illustrate that we need to, change our just y equals x plus 0 line, our initial line that we just set randomly. So our slope is 1 and our y-intercept is 0. We need to change that slope and y-intercept, or weight and bias, so that our loss reaches a minimum. And we did that using a number guessing game. And so this is our special number, and we try to guess the number, and we receive feedback on whether it's too low, too high, and we make educated guesses on what the number is. So if we know that it's too low, meaning that the difference between 12 and 1 is like too much, that loss is too much, we say, hey, we need to go up. We need to make it 5. If we make it like -1, it's not going to help us because we're going in the direction, we need to go in the direction of the decreasing loss. So if we have 5 now, the loss, which is just the square of the differences, right? The difference between the actual and the predicted, that needs to go down. We want our actual value and our predicted value to be about the same. So, we want it to be like 12 and 12. Okay, so that's when our loss is 0, because the difference between it is 0. And here, when it's 1, the loss is way too high. And yeah, we went through that example. So if you want to learn more about it in detail, then we can do that. We did that in our last video. And so how do we reach a minimum? Well, we use that using the gradient descent algorithm, which is essentially just a chain rule, and we take the derivative of the loss function with respect to the parameters, and that involves the chain rule because, you know, the loss takes in your model prediction as the input, and it also and the model takes in your real input. And so we have the parameter, you know, b, and then the model, and then fn, and it's like that. So, you know, we have a couple of different components going on. So yeah, and that's what we talked about in our last video. And we also talked about how we need a learning rate, because we can't just update our W based on the rate of change of loss with respect to W. We need, that's going to be way too much. If you subtract it by the rate of change of the loss with respect to whatever parameter we're talking about, either W or B, that's going to be way too much, okay? You're going to end up like in a situation like this, where we have, you know, too high, too low, and then you overshoot, and then you get too high. Okay, so actually we'll talk more about that today, and that's really dependent on our learning rate, which, you know, scales down this rate of change by a lot, right, by 1e2, and, you know, that's the learning rate. The learning rate is how much, or by how little do we want to update our parameters. And do we want to make, if this was a big number, then we would subtract like a lot. If it was small and we want to go slowly, which we've learned is a good thing, right? If we update our parameters too much, we're going to be, you know, doing that too high, too low thing that we talked about above. And, you know, we can't have it to be too small, otherwise it's going to be like, it's going to take forever. But we need to find a good learning rate so we can converge, right, to a minimum. And so yeah, that's where we left off. In this video, we're going to be talking about our training loop and, you know, our training iteration. And so we can either update it for a fixed number of iterations, we can update the parameters for a fixed number of iterations, or we can, you know, just keep updating until that loss converges to a minimum. So let's define our training loop. And by the way, like, we call a training iteration during which we update our parameters, right? That's the whole iterative process. If we go up to this like whole Kepler conversation, you know, we start off with an initial like 2 parameters, the eccentricity and the size, which was completely wrong because it was random. We need to, like, you know, look at our loss. We want to minimize our loss. We use a gradient descent algorithm. We minimize our loss. We try like and go in the direction of the decreasing loss every single time. And this was an iterative process to get the best eccentricity and size that actually modeled his data. So that's what we're doing. And, you know, we call each cycle an epoch. Okay, so let's define a training loop where we iterate over each data sample. Actually, we're not doing that now. We're just, you know, we're doing that now. Okay, so we're just defining the function. So when we call the function, we can enter in however many epochs we want, or what the learning rate is, or what the parameters are, etc. So we have n number of epochs, we have a learning rate, and we have our, okay, this is related to our temperature conversion example, so our temperature of unknown units and our degrees Celsius. Okay, so for each epoch, okay, in the range of like however many epochs we want to go through, so n epochs plus 1, because range is exclusive and it's like upper bound. And so we are going to set W and B equal to the parameters, assuming that we're dealing with a linear relationship, which we are. So those are going to be equal to params. Okay, so this is some tuple unpacking here. So we have W and B. Okay, and you know, we are going to say our prediction So we're defining variables here. So I guess this is tuple packing instead of unpacking, because we don't have a tuple to start out with. So TP is model, is the output of the model when we pass in the input, and W and B, which are the parameters. And our loss is going to equal our loss function, and that takes in the model output, and TC, because it needs to know the difference between the actual value and the predicted value. And our gradient is going to be, we defined a gradient function, right, which is just a vector of our derivatives. So d loss dw, d loss db, we just concatenated stuff here, two tensors using torch.stack, and we have grad fn, which takes in all these parameters. So I guess you could just copy paste it. Okay, so that's that, and we are going to be updating params, okay, in our training loop for each epoch. So you see this whole, like, for every epoch we're doing something, right? So params is equal to, or we can also say minus equals to the learning rate, which we are going to pass in as an argument when we call the function. So learning rate times grad. Okay, so that's what we're doing here, actually, above. This is essentially, our manual, sort of version of our derivative or rate of change, which we defined up here, I think. And so what we're doing below is taking that vector of derivatives, because we have two derivatives. We have one is the rate of change of loss with respect to W, and one is the rate of change of loss with respect to B. So we have that vector, and so instead of doing it for each parameter manually, we're going to take the difference. Okay, see that? Actually, yeah, instead of doing it for each parameter manually, we're going to do this instead. So yeah, and we're going to be printing what epoch it is. So just for our, just so that we can understand it, we can say epoch modulus ID. Actually, D, not ID. And this is just some formatting that's going on here. You don't need to worry about it too much. So okay, remember, loss is just a scalar. And if you're kind of confused about the different moving parts of this whole entire story, I would definitely recommend starting at the beginning, because I know this is a lot that I'm throwing at you here. Especially if you're really new to this whole machine learning process, just take it easy and go slow. Start at the beginning, and we go through an example. It's mathematical model, and this is our loss function. We're seeing we want to make that difference between our prediction and the actual value really small, and we define a few things, we initialize the parameters, and now we're updating it. And if you want to go into each of those in detail, and also the gradient descent, and finding out how we update the parameters, and all these definitions, I would definitely recommend going through my previous few videos on this whole process. So yeah, okay, print that. Okay, we're gonna have some tabs here, parameters, comma params, and let's also print the gradient. Okay, so grad comma grad. Okay, and at the end, we're going to return params. So I have a feeling that we're going to need to run all of this at the beginning. We have to start at the beginning and then, do that. Otherwise Python's going to freak out and say, hey, this isn't defined yet. So let's just run through that. Okay, good. So let's initiate this training loop. We just defined the function here. Let's actually call it on our, all our variables that we've defined. And so you see in the in this function definition, we're making use of all of the functions that we've defined previously. The loss function, the gradient function. We're making use of what we've learned about how we need to scale down what we are subtracting from params. Otherwise, it's going to be that overshooting and undershooting sort of situation. And, that's what we're doing. Okay, so let's call our training loop on our data that we've manually defined on the top. So let's say the number of epochs, let's say it's 100. Okay, and these are the sort of numbers that you're going to be dealing with. Don't expect it to be like 1 or 2. Actually, this is also this isn't that large. So learning rate is equal to 1 E2. Okay, and we'll see some problems that arise. Okay, and that's the whole point of this video, essentially, to deal with those problems. Okay, torch.tensor. Okay, 1.0 and 0.0. These are our initial parameters that we are going to use, and our training loop is going to update these. Okay, so let's say that TU, these are our keyword arguments. So let's say TU is equal to TU, and TC is just going to be TC. Okay, so this is the parameter name, parameter of the function, TU, TC, and we're setting it equal to the actual tensors that we've defined up top. So that's that, and we run it. Okay, what's going on? Okay, any epochs. Oh no. Okay, any epochs, the learning rate is 1 E2, params is equal to torch.tensor. Oh, okay. That was a problem. Did we not, okay, what am I doing? We didn't even put in params here. Okay, so this is not a new variable, this is just we're assigning it to that. So excuse me for that, and I'm sorry about that. So we're defining W and B here, and we're setting that equal to the params. Okay, we need the parameters, obviously. It's not a surprise, because that's essentially what we're updating, and so we need to pass in which specific parameters we want to look at, and so yeah. What? D loss Fn is not defined. Okay, hold on for 1 second and I'll be right back. Oh, okay, there's no underscore. That's the issue. So where was the problem? Def grad FN, okay. Okay, you'll probably see, okay, yeah, okay, good. So we see for every epoch, we get a loss, we get the parameters, we get the gradient. So we get the gradient for each of the parameters, right? So we get 2 values for each single time, right? Like I said, a gradient is just a vector of derivatives. And in neural networks, you'll definitely see a lot more, although you won't be doing it manually like this, but, you know, we see what's going on. Okay, and this is the problem we run into. We see NaN. What the heck's going on here? Well, what we did was that we did something called overtraining, okay? And our loss, like, blew up. Okay, let's look at the last values that we look here. Okay, we're seeing crazy values here. Okay, negative infinity. We're updating it way too much, okay? So you see this, like, this 5.4 E26, negative 3.18 E32, positive this 38, negative infinity, positive, whatever, okay? You see this crazy thing that's going on. What happened? Well, your params are, you know, they're receiving updates that are insane. Okay, we're not controlling it at all. And so instead of converging to a minimum, it's diverging. And the knob that we talked about in our previous video about our, you know, our number guessing game, you know, the knob is at 12. It's supposed to be at 12. Okay, where we start off at 1 and we twist it. We need to twist it slowly. 5, 9, 14. Okay, 13, 12. Okay, but what we're doing here is we're going like 1, 400. Okay, not good. Okay, let's go to 200. Okay, 600. Okay, negative 100. Okay, 500. We're going in crazy directions. We are updating it way too fast, way too much. Okay, we need smaller updates once we know that we're going in the right direction. Once we are like, if we, you know, by accident, if we go like 1 and then 440, okay, then we need to make the updates larger. But if we already know that we're going in the right direction, then, like, we don't need to go that fast. Like, you see how we're going slowly here? Like, 1, 5. I mean, I guess you might not see it because 12 in and of itself is a pretty small number, you know, but, like, if we have a larger number, you'll probably see the overshooting and undershooting, like, this oscillation that's going on here. You know, you're going up, you're going down, you're going up, you're going down. These sort of oscillations are what gets this model, like, in this sort of situation where we have NaN for, like, literally all the values. Okay, all the parameters and gradients, right? If you take the derivative of the parameters with respect to something, if you take the derivative of the loss with respect to the parameters, you're obviously going to get NaN as well if the parameters are NaN, right? So, yeah, so these are what kinds of problems, like, arise when we, update it too much. So, I feel like this, this sort of lies within the hands of, our learning rate, right? That's what we talked about. We can't update it too much, so we scale it down, right? That's what our learning rate is for. Why aren't we utilizing it to its full potential? Well, we can, and that's what we're going to do now. Okay, so we would have obviously, we would obviously choose a smaller learning rate, right? Once we realize that it's going too far. Once we're instead of like subtracting too much, right? We want to update this parameter slowly. So, okay, the learning rate is literally the most important parameter. You could argue. I mean, there are a couple of others, but it's very important. The learning rate is extremely important. And it's an extremely important hyperparameter. That's what we call it. What's a hyperparameter? Well, a hyperparameter is something that, we can change. It's, once we start dealing with neural networks, there's going to be a lot that we cannot control, especially with the math, right? But there are a couple of things that we can control that affect the entire learning process tremendously. And these sorts of parameters we call hyperparameters. And the learning rate is one of them, as you can see. Right, we can change it on the outside without, going too deep into the actual math that's going on behind this, right? We just change it in the training loop and we just change it. So, okay, it's an extremely important hyperparameter. So, okay. All right. That's the main lesson of this video. We usually change the learning rate by orders of magnitude, right? We don't just change it by like 1 or 10. We change it by orders of magnitude. So we change it by a lot. So instead of like 1e2, we might try 1e3 or 1e4. So we would decrease the magnitude of the updates, so that we get better results. So let's say training. Let's call it again. Okay, this is a markdown cell, so it doesn't actually work here. So, okay, the training loop is equal to, actually we're calling it, so, and epochs, still gonna be 100. Okay, the learning rate, let's change it to 1e. And params, once again, is just going to equal torch.tensor of 1.0, comma 0.0 for the weight and bias respectively. And we also need tu is equal to tu, and tc is equal to tc. Okay, so let's do that again. Epochs. Okay, and now we go down. Do we see any NAs? No. Okay, we're good, but not completely. Okay, we see some other thing going on. The updates are too small. Okay, so what we see is, we're seeing the loss stop at around 29 when we know we could have, gone to a much lower loss. We're seeing, okay, 29. Okay. That's like, okay, going back to our number, I'm guessing game, it's like instead of 12, if we had like 40,000 and we go like 1, 2, 3, 4. It's going to take forever, right? And the loss that you see, the difference between 1 and 40,000 and 2 and 40,000 and 3 and 40,000 doesn't change significantly, which is why we get the same loss, right? If our updates are too small. So, 29.028. You see it's going down, right? 028, 027, 026, 025. It's going down, but it's not going down at the rate that we want it, which, we got to change our learning rate for again, right? But we have another problem. We see the gradients here. Okay, wait. Let's go at the top. the gradients you see here are of different magnitudes. Okay, so the derivative of the loss with respect to W and the derivative of the loss with respect to B are of different magnitudes. And the thing is, we're updating the parameters like together, right? We're updating it by the same amount. The learning rate is the same. And that's a problem, right? Like if we, like the way we're updating it, the way we're going up and going down in the direction of the decreasing loss, the way we're doing it for one parameter might be good. It might be, we're not updating it too slowly, and we're updating it by like right amounts, right? Especially if we have a long way to go, right between 1 and 40,000. If we have a long way to go, it's good. You can make those updates a bit larger instead of going 1, 2, 3, 4. But if the range of the slope is like 1 to 40,000, and the range, I'm just making numbers up here, but like if the range of the bias is, maybe 1 to 100 instead of, 1 to 40,000, we can't go up by the same amount. We can't update our parameters by the same amount, okay? Because the weight and the bias are different. They have different requirements and they have different needs. And so how do we solve that problem? One possible solution is that we have different learning rates for each one. Okay, so we update it differently. But once we go outside the realm of linear relationships, that's going to be really hard. We have hundreds and thousands, maybe even millions of parameters, right, that we need to update. We can't have a different learning rate for each one. That's going to mess things up. Another solution, which is a bit more, realistic, is changing the values themselves, right? Changing the inputs so that the gradients aren't that different. Negative 0.05 and 3.0, they're really different. Actually, not the gradient, the parameters, right? 0.2 and negative 0.2. Or like if you go up, 0.5 and negative, they're different. Okay, so we need to be able to, you see 4,582. Okay, we need to change the inputs so that, this sort of information is the same. Okay, so the gradients, we don't want the gradients to be that different. Okay, because the gradient is what we're basing our updates on, right? We're updating based on the rate of change of the loss, right? So we need to keep that in check. Not only the learning rate, but also the gradients themselves, right? That's the big driving factor. And so what we can do is we can normalize the data. We can normalize the input so that the gradients aren't crazy, so that no matter, even if your learning rate is off by a magnitude or 2, we're not going to see crazy results, okay? So if we normalize the inputs, the gradient is the biggest, factor, deciding factor. And, we can normalize the data between, negative 1 and 1 so that the derivatives won't be that different. And, yeah, we can achieve something that's close enough by, multiplying TU by, 0.1. So that's the normalization that's going on here. So normalization is just like when you scale the values down to a certain range, so that it's more manageable. Okay, so we can say TUN, which just means T, temperature, unknown units, N stands for normalized. So let's just say that it's, 0.1 times TU. Okay, and the training loop Now let's see how things go. Okay, so n epochs, still 100. The learning rate, maybe like 1E2, okay? We're not making it as small as we did. Let's see whether we have different results, okay? Just because we changed and normalized the inputs. Okay, let's see if that makes a difference. So params is still going to be our torch.tensor. 1.0, 0.0, and those are the default values, right? Because this line is just y equals x, right? If the slope is 1 and the y-intercept is 0. So TU is not just TU, it's TUN. So it's a normalized version. And TC is just TC. We can't change the actual value, right? So yeah, let's see. Let's run it. What's the syntax error? The parentheses are good. This is good. This is good. Oh, comma. Okay, so we ran this. Okay, fix that little syntax error. And we run this with IE2. And we start off with a loss of 80, so we were really wrong at the beginning. 29, 28, 27, 26, okay, a lot better. 25, okay, we never got to 25, we never got to 23, okay, 22, okay, this isn't perfect, but it's a lot better than what we had before, right? So they're not blowing up this time. They're not staggering it, like they're not staying at one value, even if we didn't make that learning rate super small. And this is the impact of normalization. And some people might argue that you didn't really need normalization to get to this point, but we could have found ways around it and things like that. But this illustrates the problem that we have, okay, and it offers one potential solution. So the problem is that it blew up. The other problem is that it stayed at one spot, and by it I mean the loss. Those are the two problems that you can encounter, and normalization is one way to tackle that. Okay, so yeah, and let's try this with without printing the parameters, and let's try it instead of with 100. Let's try it like with 5,000 epochs. So it's not going to be a good idea to print every one, because that's gonna take a while. But if we copy this function and we redefine it below, let's just call it with no printing. I mean, we're still going to print the number of epochs and the loss, but we're not going to be printing the parameters. No printing parameters, params. Okay, and we do the same thing, except at the printing stage we don't print everything. So let's just print the epoch and the loss. We don't need to print the parameters or the gradient. Okay, and let's define that, and let's call the training loop printing no params. And let's just copy this because it's essentially the same. And let's say 5,000. Okay, now you'll see, okay, because it has more chances to update. Okay, it has, every time you run through it, you update it. So if you run through it 5,000 times, you're updating it 5,000 times. And let's see if we can minimize the loss there. Okay, so we're starting at 80, 19, 15, whoa. Okay, 11, 10, 9, 8, 7, 6. Whoa, we're getting a loss that's really small. Okay, maybe let's scroll down like that. 2, and we didn't actually get to 0, but see how close we got. We got to 2. Maybe if we increase the number of epochs again, maybe that would have solved actually, we don't have any problem, right? Maybe that would have gotten it to 0. Maybe if we make the learning rate smaller, or, change up some little things. But yeah, you see, now you really see that the loss is getting really small, and we're getting closer to this stage in our, number guessing game, where we're really close, right, to the secret number 12, and, we're almost at 12, and, if we just fix the little things here and there, we can, get to we can get to this, like, perfection. Okay, so, yeah. And our unknown sort of units kind of look like Fahrenheit, don't they? So these are our unknown units are actually in Fahrenheit, degrees Fahrenheit. And you probably knew that at the beginning, but now we can see that for ourselves using this whole machine learning process. Okay, and thank you so much for sticking with me throughout this whole, intuitive understanding. In our next video, we are going to be talking about, AutoGrad, which is PyTorch's way of automatically computing the derivatives, and we'll see more about that in our next video, but hopefully you'll appreciate that more now that we see how much work goes into this. But now we know that our whole process works, and our loss is getting smaller and smaller. That means our mathematical model is really updating our weight and bias, accordingly, and getting closer to that y equals mx plus b that really represents that relationship between not Celsius and an unknown temperature, but Celsius and Fahrenheit. Okay, so thank you so much, and don't forget to like, comment, and subscribe. I hope you learned something new, and I'm looking forward to seeing you guys in my next video.